Okay, so when we're talking about energy, okay, we have to look a lot at what happens to it when it's transferred or converted, okay, because that happens a lot. Okay, anytime you do work, you're transferring mechanical energy from one object to another. Like, for example, if something was on the floor and I lifted it up and put it on a desk, I've done work. Okay? I have given that object potential energy, thus mechanical energy. So it's gained it from me, right? That's work. I've transferred mechanical energy to it. If thermal energy moves from one object to another, that's heat. Okay, and heat is the flow or transfer of thermal energy. Right, so that's what we're going to be looking at here. Okay, so we're going to learn some terminology and things like that. All right, so the first bit of terminology that we want to talk about are the types of systems and what a system is. All right, so very simply, a system is a set of interconnected parts. All right. Now that doesn't necessarily, you probably get in your mind like a picture of an engine or something like that that's got a lot of moving parts that are connected by gears, but it's not always that complex. Okay. A system can be as simple as me and this room. Okay. I'm going to be losing thermal energy to the surroundings of this room. Thus, we're an open, or I'm an open system, or that's an open system because I'm exchanging matter as well as energy with my surroundings. Everyone okay with that? Okay, so we're a series of connected parts. Okay. So in studies of work and energy transfers, a system is the object or objects involved in the transfers, and everything else is considered the surroundings. Okay, so the system is the object or objects involved in the transfer, okay, and everything else is considered to be the surroundings or the environment. So surroundings is also a term, okay, that we need to know. All right, so in the diagram there, this person is not very smart. Okay? They're holding a metal rod in a fire. Okay, so the caption there is saying heat flows from the fire to the metal rod. Yes, it does. And it flows through the metal rod to the person's hands. Okay, metal tends to be a good conductor of heat. That is, it transfers thermal energy very easily. And you would not want to hold onto a metal rod while you were holding it in a fire because it will definitely get hot and burn your hands, and it'll do so fairly quickly. Okay, but this is an example of a system. There's the fire, there's the rod, there's the person. Okay, there are a series of connected or interconnected parts. Okay, and energy is able to flow between them. All right, so the three types of systems that we're going to look at are open systems, okay? And in an open system, both matter and energy are exchanged. Okay, so I'm an open system because I'm exchanging matter and energy with my surroundings. Okay, I'm breathing in and out, so I'm exchanging matter. Okay, oxygen, carbon dioxide, water vapor, whatever. Okay, and I'm exchanging energy. The air is only 21 degrees. My body temperature is 37, so naturally energy is going to flow from my body to the surroundings. Okay, you may have noticed that in January and February when it was really cold, my classroom was really cold. Okay, I saved the taxpayer money by allowing the second law of thermodynamics to heat my classroom. That is you guys. Energy naturally flows from you guys and into my classroom. Right? You'd be surprised just how much. Okay, because by period 4, after I've had 3 classes in here, okay, the temperature in my classroom is 4 degrees warmer, usually, okay, which is a real problem when it's June. Okay, because in here it can become 28 or 29 degrees, especially on a day when there's an exam and there's a lot of stress. There's way more heat being transferred on those days, okay, and the room gets noticeably warmer on those days. All right, so does everyone understand what an open system is? Okay, so it can exchange matter and energy, so it's just wide open. Okay, so the Earth is a system, okay, and the universe is its surroundings. Earth is an open system since it exchanges both energy and matter with its surroundings. Okay, a closed system is one that cannot exchange matter, but can exchange energy with its surroundings. So if I take anything and seal it in an airtight container, okay, that airtight container and whatever is inside have become a closed system. Right, so let's say that it's leftovers. All right, so I've just eaten my supper and I've got some leftovers. I put them in a Ziploc bag or in an airtight container, okay, and I put them in the fridge. They're still warm. They're definitely warmer than the fridge, but they're not exchanging any matter with the fridge, okay? The air that's in the container stays in the container. The food that's in the container stays in the container. They don't interact that way, but it definitely transfers energy to the fridge, which then transfers it to the room, okay? That's how a fridge works, okay? It absorbs the energy from the objects inside and then pumps it out into its surroundings to keep them cold, right? We'll talk about how that works in a little bit as well, right? So that would be a closed system. An isolated system really can't exist, okay? But we pretend like they can, okay? It is one that cannot exchange either matter or energy with its surroundings. It's quite easy to make a closed system and prevent the exchange of matter. It's another thing entirely to completely prevent the exchange of energy. Okay, so if I have like my coffee cup here is a pretty good insulator. Okay, if I'm using this, my coffee can stay warm for hours. Okay, I've in fact some days had sips of my coffee in the afternoon and it's still warm, and I make it at like 10 to 7 in the morning. Right, so it's pretty good. But if I left it here overnight, came back the next morning, is it still going to be warm? No, it's a closed system, not an isolated system. It is still slowly bleeding energy away to the surroundings. Okay? To completely isolate something would mean that it cannot exchange any energy, can't receive it, can't give it to the surroundings. And it's pretty much impossible to do that. Okay? Everybody with me on that? We pretend like we can because it makes the math of a lot of things easier when we're first learning about them. So lots of times you'll see the term in an isolated system, or assuming this is an isolated system, that basically means no energy is getting put in, no energy is coming out. Right? It doesn't really ever happen that way, but it makes things a little simpler. Kirsten, you had a question? You had a question? You were going to say something? No, no. As far as we know, it's like if you had a perfectly isolated system, you'd effectively have built like a perpetual motion machine. Would be an isolated system because it would never lose energy to the surroundings. That's why you can't make one. They all stop eventually because they all are losing energy to the surroundings in some way, sound, heat, whatever, right? There's always friction that's taking some energy away. It's impossible to make something frictionless. Okay. Yeah, even like the International Space Station is not an isolated system. It's a closed system, right? It's not exchanging matter with the surroundings, but it is always exchanging energy. It's got solar panels that are receiving energy from the sun, but it's also losing heat all the time to the vacuum of space. Right? Okay. So first law of thermodynamics and the law of conservation of energy. I like to cross this out and write is the law of conservation of energy. Okay? Because the first law of thermodynamics basically states that energy can't be created or destroyed. Okay? Now, another important thing that's in here is distinguishing heat from work. Heat and work are similar in that they are both transfers or exchanges of energy. What's different is the type of energy they exchange. All right? Heat is a transfer of thermal energy. Work is a transfer of mechanical energy. All right? So this sentence here is really important. Work involves the movement of matter from one location to another. That's mechanical energy. Okay? Whereas heat is a transfer of thermal energy from one location to another. Okay? So I can change the energy of a system by doing one of two things. I can do work on the system, which means I make some of the parts of the system move faster or slower, or I add heat or take heat from that system. Okay? That means I'm taking thermal energy or adding thermal energy to the system. Either one of those two things will cause a change in the total energy of a system. Okay? Because they are both transfers of energy. Right? Really, those are the only two ways that I can change the energy of a system. Do work or do heat. I know it sounds weird to say do heat, but it's true. Okay? Use heat or give heat. Okay? All right, so the energy of a system can be increased in two ways. Either heat can be added, okay, or work can be done on the system by its surroundings. Okay? So this paragraph here, okay, is important in that it talks about how heat and work, okay, can change the energy of a system. In this case, it's increase, but decrease would just be the opposite. Let the system do work on something else and it'll lose energy, right? So for example, if somebody, if there's like a cart on wheels that's moving by me and I stick out my hand and kind of slow it a little bit, okay, it's done work on me because now it's moving slower and has less mechanical energy. Okay? And I have a little more because as it goes by me, I'm going to turn a little bit as I slow it down. Everyone kind of follow on that? Okay. If I'm talking about a campfire, okay, I'm going to take heat from that by putting a pot of water over it and allowing the water to increase in energy. So the campfire system is losing energy, the water is gaining it. Okay, so the first law of thermodynamics is kind of highlighted here for you. Okay, it's really just a restatement of the law of conservation of energy. Okay, so this law states that the total energy, including heat, okay, in a system and its surroundings remains constant. Whenever heat is added, it transforms into equal amounts of some other form of energy. Okay, or when work is done, same thing. Okay, so if we're looking at these two things here, so this girl who was holding the rod over the fire a few minutes ago has now put the rod in a pail of water, right? So what's going to happen to the water? It's going to heat up, right? And some of it like evaporates really quickly, like it sizzles when you put it in there, okay? And that's showing that, yeah, I'm adding energy, I'm adding heat to that pail of water, all right? So that's one of the ways to increase the energy, the total energy of the pail of water, okay? This person is changing what kind of energy? Yeah, potential, kinetic, mechanical, right? Because that's what they add up to. So by jumping up and down on the pogo stick, okay, they're changing their kinetic energy into kinetic and into elastic potential energy when they stretch the bands or compress the spring, whichever that one looks like it's an elastic band one, okay? So we're changing that energy, okay? When I first jump onto the pogo stick, I add energy to it. Okay, and I continue to do that as I continue to jump. Okay, I'm putting energy into that system. Right, it gives it back to me because it's elastic. Okay, if this was an isolated system, I would only have to jump on the pogo stick once, and after that, the pogo stick would hop on its own with me on it forever. If it was an isolated system, but it's not. Okay, so I jump on that pogo stick and it might bounce twice, and then I've got to start putting energy and I've got to work, okay, to keep it moving after that. Has anyone ever used a pogo stick? They're kind of like dead now. You don't see them much. What's that? Yeah, yeah. Yeah, it's not something. It's like riding a unicycle. You don't just jump on it and go, "Hey, I can do this now." Okay. Yeah. All right. So is everyone following the difference there? Thermal, like heat, is a transfer of thermal energy, but work is a transfer of mechanical. Okay. So yeah. So this is what happens, like we said, in most real world situations. Most machines have many moving parts that are in contact with each other. That produces friction, and friction usually results in a loss of energy through sound, light, and heat. Okay. So even though some energy is lost to heat, the law of conservation of energy still applies. The total amount of energy is all still there. It's just not doing anything useful. It's become heat and it's gone out into the surroundings. Okay. The big thing is that you can't create energy and you can't destroy it. You're always converting it from one form to another or transferring it to something else. Okay. Yes, it looks sometimes like you're losing energy, but it's just being turned usually into heat, which then doesn't do anything useful. Okay. All right. So perpetual motion machines. Okay, we talked about these just briefly a minute ago, right? But you can't make one. And even if you could, what would a perpetual motion machine be able to do? Like, if I could make a perpetual motion machine, could I hook it up to my house and use it to power my house? No. Well, no. As soon as I hooked it up to my house, it would stop. Okay? A perpetual motion machine can run forever, but that's all it can do. it can't do any work, because as soon as it does work, what is it doing with its energy? Giving it away. And as soon as it gives it away, it'll stop. Okay, so even if I could make a perpetual motion machine, which I can't because it would be then an isolated system, there would be no friction, it would be completely silent. Okay, if you were to actually make a perpetual motion machine, it would make no noise at all, because noise is a form of energy. And if it made noise, it would eventually stop. Okay, and that's what happens with all even highly efficient machines. Okay, they're always losing energy in some form. All right, so we can't do that, and even if we could, they wouldn't be able to do any useful work because they can't transfer mechanical energy away because there's no energy being put into them. Okay? If I could hook up, if I had a perpetual motion machine, I hooked up to my house and it powered my house, not only would it be a perpetual motion machine, it would be magic, because it would be doing what with energy? Creating it, yeah, and you can't do that. Okay? You can't create energy from nothing. Right? There has to be some initial source of energy that's being converted. Okay. All right. So perfect machines or perpetual motion machines, like we say, can't be built, and they can't be built because of the first law of thermodynamics, but they also can't work because of the second law of thermodynamics. Okay. And the second law of thermodynamics says that energy flows from high energy to low energy, or from hot to cold, depending on what kind of energy you're dealing with. Energy always flows away from the high energy object. Okay, so the first and second laws of thermodynamics basically prevent, okay, the development of a perpetual motion machine. Right, so these were some examples of perpetual motion machines that people thought they could make. Right, like this one here with the curved pi sectors. Okay, they figured that if it could turn, then the ball would always roll to the outside, gravity would pull it down, which would cause it to spin, and then as it spun, the ball would go back towards the middle as it rotated over the top and then continue to fall, except eventually this will stop because of, well, no, gravity is actually what would keep it going if it could work. Friction. Yeah, there's a pivot point in the middle. There's a spot where two solid surfaces are interacting and rubbing against each other. That's going to produce friction and the thing would stop. Okay. This one here, it's got potential because it's using a magnet, but eventually magnets demagnetize, eventually. Okay, but it could, yeah, pull up a metal ball. The metal ball could fall, come back down here. But the thing of it is it's always got to do what with this door? Open it. And opening that door is work. Okay, so it would lose energy. Okay, eventually they're going to get stuck here and not be able to open the door, right? And then the machine will stop. All right, so the big thing here, second law of thermodynamics, describes the direction of energy flow in natural processes. It says that heat always flows naturally from a hot object to a cold object, but never naturally from cold to hot. You cannot transfer coldness, is what the second law of thermodynamics says. You can transfer heat, but you cannot transfer coldness. All right, which is weird because we think we can. We think that's what a refrigerator does or an air conditioner does. It transfers coldness. Actually, it doesn't. Okay, what it does is it uses energy to pump heat into an already hot area. Okay, we call a refrigerator or an air conditioner a heat pump. They're effectively active transport for energy. Okay? Back in biology, we said active transport is pumping something against the gradient, right? Making it more concentrated in one place. Well, a heat pump like a fridge or an air conditioner is doing the same thing. Right? If you've never noticed, okay, if you like put your hands near the bottom of your refrigerator, okay, where the vent is, you'll feel warm air coming out from it. Okay? That warm air is the heat that's being absorbed from the stuff in your fridge. It's being pumped out of the fridge and into the surroundings. That takes energy. All right, and we'll show you how that works. It usually involves a condenser and using some sort of refrigerant. Okay, but it takes energy to do it because it wouldn't flow that way naturally. All right. Okay, so the first idea, okay, and this was like Young and Black and those guys that were kind of working on this idea here. Okay, and Sadi Carnot was the first person that developed one of these, is a heat engine. Okay? The heat engine uses the natural flow of energy from hot to cold in order to do work. Okay? If I know energy is naturally moving from hot to cold, I can make matter go with it. And if matter is going to move, I can make matter do work. Okay, because moving matter is mechanical energy. Everyone okay with that? Okay, so what their idea is if I have a high temperature area and a cold area or a low temperature area, and I put something in the middle, as matter and energy flow through it, it'll do useful work, which I can take this way. Okay? And we use this all the time. This is how a jet engine works. Okay? A jet engine works, okay, by having, the fuel being burned in one place, and as the fuel is burned, the heat pulls air with it through the engine and turns the turbine, which creates thrust. Okay, and that's how a jet engine works. It's got a really hot area where the fuel is burned, and the surrounding area is very cold, especially when the jet is at high altitude. Okay, jet engines typically work much better in very cold conditions because there's a bigger change or difference between hot and cold. Okay. All right, so when the heat in a heat engine flows from high temperature to low temperature, that heat can be converted to mechanical energy, which can do work. Okay, so that's how a heat engine works. Okay, so a heat engine is a device that converts heat into mechanical energy. However, only some of the input heat can be converted to mechanical energy. The remaining heat is expelled as exhaust. All right, they're not super efficient, is basically what we're saying. Right? So in an internal combustion engine, like we would have in our car, okay, the fuel in the combustion chamber burns at high temperature, and that causes the gases inside the piston or inside the cylinder to expand. And when they expand, they push on the piston and push the piston down. That's where they're converting heat into mechanical energy. The expanding gases push on a piston, which can then turn a crank, and that's your change to mechanical energy. Everybody follow me there? Okay. When that happens, though, it makes a lot of heat that doesn't do any useful work. Okay? Your car actually uses almost a third of the energy in its fuel to keep it from melting down. Okay? Almost a third of the energy in your fuel runs the cooling system on your car. That is the water pump and the radiator, okay, that are trying to radiate the heat away from the engine to keep it from destroying itself. Okay? So most of that heat that's actually used to make mechanical energy doesn't end up making mechanical energy. It just ends up being wasted. It goes out the tailpipe or it goes out the radiator, okay, and it has to be vented away. All right, so this was the first idea for a heat engine, that it would be used on a boat. So there would be two pipes. One pipe would be very short and up near the surface of the ocean in where the water would be very warm. Okay, because the sun is hitting it. Obviously, hot water rises, same as cold water, same as hot air and cold air. Okay, and then there'd be this really, really, really long pipe that would go way, way down to the deep ocean where the water is very cool. Okay, and then water would naturally flow through the engine from hot to cold. This is wonderful in theory, but in practice, it just doesn't work. What's the motivation for this water to go through the engine and then down through the pipe into the cold water when it could just go there directly? There isn't. It just doesn't work. Okay. And then there's the practical side of this. I don't want to be driving a boat that's got a big long pipe hanging out the bottom of it because it's going to hit something. It's going to drag bottom or whatever. Okay. You don't want a big long pipe. It's essentially an anchor. Okay? It's just not practical. The design was never ever used. It was just theoretical here. This could work. Okay. And they're right. It could work. The issue is that there's not enough of a temperature differential between the warm water and the cold water to really generate any thrust anyway. But in a jet engine, it works very well because we're talking about a fire that's, several hundred, maybe even 1,000 degrees Celsius and surrounding air that's, minus whatever. Okay? There's a huge temperature differential. The air moves through these turbines that are very light, okay, very easy to turn, and can generate a lot of thrust. Okay? So that's kind of how that would work. Right, so that would be your jet engine. Okay, you can see here, you can see the turbines and little fan blades, okay, that create that thrust. All right, I'm going to leave it there. We'll talk about heat pumps tomorrow, okay, because I won't get into those today. You will not have a quiz tomorrow. I haven't taught you enough for you to have a quiz, so no quiz tomorrow.